In this video, we're going to do the first of many challenges. Now, I tried to make these challenges align with what we've already learned, but in some cases the solution requires a new function or trick that we haven't discussed. Now, that's on purpose because in the real world, the problems you come across aren't limited to the things you've already seen. So part of being a good data scientist is having the ability to search for a solution online and to read and interpret documentation. So I'm going to encourage you to do all of those things in your attempt to solve these problems. All right, let's get started on the first challenge. With your high school reunion fast approaching, you decide to get in shape and lose some weight. You record your weight every day for 5 weeks, starting on a Monday. Given these daily weights, build an array with your average weight per weekend. So here's the setup. Basically, I just import NumPy, and then I build an array of weights. So this weight here was recorded on a Monday. So then you have Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So your solution should be a 5-element array, 1 element per weekend, where, for example, the first element in your resulting array should be the average of these two values because this is the first Saturday and Sunday. It's the first weekend. So go ahead and pause the video and see if you can solve this problem. All right, so as they say, there's 1,000 ways to skin a cat. Here's the solution that I came up with. So let's go ahead and break this apart. So this piece here gives me the weight on every Saturday. And the way to read this is it's saying start at index 5, go until the end of the array because we leave the stop parameter empty here, and step by 7. So this is just basic slicing. And if we step by 7 starting from this value here, that's going to give us our weight on every Saturday. So then we can basically just copy that and tweak it to get our weight on every Sunday. And now we have 2 same-sized arrays, so we know we can add these together and their elements get added element-wise. So this gives us like the total weight per weekend. And then we can just wrap that in parentheses and divide by 2. Remember, this division gets applied to each element of the array. And that gives us our average value per weekend, which is our desired solution. After binge watching the Discovery Channel, you ditch your job as a trial lawyer to become a gold miner. You decide to prospect 5 locations underneath a 7x7 grid of land. How much gold do you uncover at each location? So here's the setup. You get 2 matrices. Gold is the 7x7 grid of land that says how much gold is under each location. And lokes is the prospect locations. So for example, the first row here indicates that you're going to prospect under row index 0, column index 4, which corresponds to this value in the gold matrix. Go ahead and pause the video and see if you can figure out how much gold you'll get at each prospect location. All right, so here's the solution that I came up with. Let's go ahead and break this down. So the first prospect location is 0, 4. So how would we determine how much gold is under this location manually? Well, what we can do is we can say gold, square brackets, and then just plug in row index 0, column index 4. And if we want to figure out how much gold is under the next prospect location, we can do essentially the same thing, except we'll use row index 2 and column index 2. And we get back 6. That's going to be this guy here. So how would we do this in one fell swoop? If you remember, what we can do is we can say gold square brackets and then pass in a list of row indices and a corresponding list of column indices. So in this case, our row indices are going to be 0 and 2, and our corresponding column indices are going to be 4 and 2. And this gives us the array 2, 6. So now the question is, how do we do this dynamically instead of manually? Well, notice that this list of row indices corresponds to the first column of lokes, and this list of column indices corresponds to the second column of lokes. So the real question is, how do we get back the first column of lokes as a 1D array and the second column of lokes as a 1D array? And the way we can do that is we can say lokes square brackets colon comma 0. And this essentially says, give me every row from the lokes array, but only the values at column index 0. And then we can make a little tweak to get column index 1. So now all we have to do is take this as a framework and then overwrite our row indices with this guy and overwrite our column indices with this guy. And that gives us our desired solution. You decide to invest in a series of billboards along Interstate 10 to advertise your stylish new chicken restaurant, Chic-fil-A. You buy 3 billboards evenly spaced, starting on mile marker 17 and ending on mile marker 28. Then you buy another 3 billboards evenly spaced, starting on mile marker 32 and ending on mile marker 36. In order from mile marker 17 to 36, your billboards display these ads: ABC, CBA. Determine how far each C ad is from your restaurant, which is located at mile marker 30. All right, so here's my solution. Now let's go ahead and break this down. So let's start by thinking about the first 3 ads. They're evenly spaced between mile marker 17 and 28. So it'd be useful if we had a tool that gave us an array of evenly spaced numbers from a start point to an end point. So let's go ahead and search Google to see if something like that already exists. So we'll say NumPy array of evenly spaced numbers. And sure enough, there's a function called linspace that returns evenly spaced numbers over a specified interval, where you give it a start, stop, and num parameters. So let's go ahead and play with that for a little bit. So I'll say np.linspace, and let's set start equal to 0, stop equals to 10, and num equal 5. So in this case, we get back a 5-element array from 0 to 10. Notice that the start and stop values here are inclusive. Now, another thing we can do is the start and stop values can be array-like values. So for example, I can set start equal to the list 0, 5 and stop as the list 10, 15. And in this case, I get back a 2-dimensional array where each column is a sequence. So for example, the first column is the sequence from 0 to 10, and the second column is the sequence from 5 to 15. Now, another parameter for linspace is axis, which by default is 0. And that means that these sequences span axis 0, the row axis. Personally, for our setup, I think it's a little bit more intuitive to use axis 1, where we can think about the billboards spanning the columns of this array. So if we want to make this match our framework, our problem, we can set the start parameters here as mile marker 17 and mile marker 32, and the stop parameters as mile marker 28 and mile marker 36. And of course, num in this case needs to be 3. So this array here represents billboards A, B, C, CBA, and where they're located. So now if we want to get the distance from each billboard to our restaurant, which is at mile marker 30, we can just take this and subtract 30. And this is close, except that we don't like negative values for distances. So let's see if NumPy has an absolute value function. Of course it does. Notice that there's a shorthand np.abs. So what we can do is we can just wrap this in np.abs, and this gives us back the absolute value or the distance from each billboard to our restaurant. So then the last thing to do is, well, we want to know how far each C ad is from our restaurant. Well, the C ads are going to be located here and here. So we just have to pick out the indices for those guys. So in this case, what we can do is we'll pass in a list of row indices and a corresponding list of column indices. So the row index for this guy is going to be 0. And the row index for this guy is going to be 1. And the column index for this guy is going to be 2. And the column index here is going to be 0. And then that gives us our desired solution. In this problem, you're a relationship scientist, and you've developed a questionnaire that determines a person's love score, a real valued number between 0 and 100. Your theory is that two people with similar love scores should make a good match. Given the love scores for 10 different people, create a matrix where element ij gives the absolute difference of the love scores for person I and person j. All right, so here's the solution that I came up with. And before we break it down, let's go ahead and do np.set_print options. We'll say line width equals 999. So here I've told NumPy not to wrap a line of text unless it exceeds 999 characters. By default, I think it wraps after 75 characters. Now, in general, the set print options method is pretty handy, and if you dig through it, you might find some print options you want to change to suit your personal preference. So now let's dig into the actual logic of the solution. The trick here is really about broadcasting. If we could restructure the love scores array into a vertical column like this, in other words, a single column of a 2D array, and then subtract a row of love scores like this, the result will broadcast into a difference matrix like this. Here, the ij value in the difference matrix corresponds to the ith value in the column minus the jth value in the row. And from there, we can just use np.abs to get the absolute difference between pairs of love scores. So the question is, how do I restructure the love scores array as a column and a row? And the key there is to give love scores a new axis using np.newAxis, or alternatively the keyword none. So if I say love_scores, open square brackets, colon, comma, none, it gets a new last axis. In other words, it goes from a 10 by array to a 10 by 1 array. And if I do love_scores, square brackets, none, comma, colon, it gets a new first axis, and it goes from a 10 by array to a 1 by 10 array. So then I can just subtract these and take the absolute value to get the desired result. Also note that I actually don't need to promote this guy to a 1 by 10 array. I could just leave it as a 1D array like this, and NumPy will promote it for me. But personally, I kind of like being explicit about it because I think it makes it more obvious what's happening. You're a vindictive, hateful professor, and one of your pet peeves is when students rush through their exams. To teach them a lesson, you decide to give zeros to the first 3 students who score less than 60 in the order they turned in their exams. So, given a 1D array of integers, identify the first 3 values less than 60 and replace them with 0. All right, so here's the solution that I came up with. Let's go ahead and break it down. So before I explain it, I need to rebuild my scores array. And now let's just start with this part, scores less than 60. So this is pretty straightforward. This just determines whether each score is less than 60, and it returns a Boolean array. So now the guys we're interested in are the true values. Those are the people who scored less than 60. And what would be useful is if we could get the index of each true value. So NumPy has a handy function called non-zero, which returns the indices of elements that are non-zero. So if I have an array like np.array, open parens, square brackets, 0, 1, 2, 0, and I call dot non-zero, it spits back a tuple with indices for the non-zero elements. So in this case, indices 1 and 2 have non-zero elements. Actually, let me make this 3 and 4 just to make this a little bit more clear, right? So it's indices 1 and 2 have non-zero elements. So the reason it returns a tuple is if you have a multi-dimensional array, like let's say, for example, you had a 2D array, each element of the tuple would return an element that corresponds to a single dimension. So for a 2D array, the first element of the tuple would give the row indices, and the second element would give the column indices corresponding to those non-zero values. So in our case, we just have a 1D array, so we get back a tuple with one element, which looks kind of stupid, but that's why. So we can actually apply this non-zero function on this array of Boolean values because Boolean values, well, false and true are synonymous with 0 and 1. And you can use them with multiplication, division, functions like non-zero. It comes up as a super useful trick in many circumstances. So what we can do is we can say scores less than 60 dot non-zero. And this gives us a tuple where the first element has the indices of these true values. Again, true is 1, false is 0. So then if we just do square bracket 0, we can pick out that array. So now we're getting back the array of indices with true elements. And then we want to get the first 3 people, the first 3 true elements. So the first 3 people scored less than 60. So we can say square brackets :3, which means give me every element up to but excluding the third index. And now we have the indices for those people. So now we just need to say scores, square brackets, and then identify those people and give them a big fat 0. Now if I print my scores array, you can see that it updated as we wanted. Eager to make your mark on the PTA, you decide the best way to hide eggs for the upcoming Easter egg hunt is to use NumPy. You represent the field as a 10 by 10 array of zeros. Now your goal is to insert 20 random normal values at random, non-repeating locations in the grid that tell you how much candy to hide at each spot and where. Here's the solution that I came up with. Before we break it down, let me rebuild the field array. Let's start with the easy part. So we need to fill 20 eggs with a random amount of candy based on a normal distribution. So we know how to do that. We can start by building a generator, and then we can say generator dot normal size equals 20, and that gives us 20 random normal values. Now I'm going to clean this up a little bit, so I'll wrap this with np.round and round each value to 2 decimal places. And let's assign that to a variable called vals. All right, so the hard part to this challenge is really how do we map these values into unique locations in the field array? So imagine that we assign a unique value to each location in this array. So we'll say this is value 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on up to value 99. So then our goal is to randomly select 20 values between 0 and 99 without replacement. Well, we know how to do that. We can use the choice function for that. So we can say logs equals generator.choice, and we want to sample values between 0 and 99. So we want to sample the 100 values starting at index 0 or value 0. We want to sample 20 values, and we want to do it without replacement. Now to make this a little bit more dynamic, we can say field.size, that's the number of values in the array, and len vals. So we want the number of locations to match the number of candies that we have. And then let's go ahead and print logs. Okay, so now we've selected 20 random non-repeating locations. So now the challenge is, how do we get these candies into these locations that we've kind of just made up? Well, it turns out there's a function called ravel, which frankly I think should have been called unravel. And what it does is it takes a multi-dimensional array like this and flattens it into a one-dimensional array like this. And you could do this in different orders. By default, it uses row major order, which is exactly the system that we've described. So what we can do is we can say field.ravel, and let's just take a look at this real quick. So there's the flattened 1D array. And one thing to note is that in general, this does not return a copy of the field array, but it also doesn't modify it. This is what's called a view, and we'll talk more about that later. But basically, if I print the field array, notice that it hasn't changed. It's still a 2D array. So this is just like a temporary view that we can use. So we can say field.ravel, and then we'll pass in our lokes as indices, and we'll set those values equal to the amount of candy. So now if we print field, you can see that it mapped the candy amounts into these locations of the 2D array field. You're given a 10 by 2 array of floats where each row represents a movie. The first column represents the movie's rating, and the second column represents the director's rating. Your goal is to create a third column to represent the overall rating. The overall rating is equal to the movie rating if it exists, otherwise it's the director's rating. Okay, I came up with 2 solutions to this problem, so let's go ahead and take a look at the first solution. Let's break it down. So here we use the where function, and we basically say where the first column of the ratings array is nan, go ahead and use the value given in the second column. Otherwise, use the value given by the first column. And we assign that to a variable called x. So if I just print x here, you can see this gives us the values that we want to insert into the third column. So then the challenge is, how do we put these values into the ratings array? And for that, we can use the insert function. So we say np.insert, and we pass in the array we want to insert into, the values that we want to insert. So in this case, x, the array we just created, the axis, so we want to insert it as a column, so axis equals 1, and then the location, so object equals 2 means we want to insert these values at index 2 of axis 1, in other words, the third column of the array. And then we assign that to a variable called result. So note that the insert function doesn't actually modify the ratings array. If I print ratings, you can see it hasn't changed. So we return this copy with the new column inserted into a variable called result. Here's the second solution that I came up with. So it starts out just like the first solution, where we define x as the new values that we want to insert into the last column. And then we use the hstack function to horizontally stack the ratings array with x. Now the trick here is the ratings array is a 2-dimensional array, so we need x to become a 2-dimensional array to make it compatible for stacking, and we can do that with x square brackets colon comma none, where we give it a new last axis. If you want to see what that looks like, it basically looks like this, and that's what makes it compatible for stacking with this ratings array, and then the result is what you'd expect. 10 fish occupy a 5 by 5 by 5 grid of water. Each fish decides to move to a new IJK location given by the matrix below. If multiple fish end up occupying the same cell, the biggest fish eats the smaller fish. Determine which fish will survive. All right, here's the solution that I came up with. Let's break it down. So imagine we assign an ID to each fish, where the IDs are simply 0, 1, 2, 3, 4, and all the way up to 9. Then we can start by sorting the IDs based on weight from heaviest to lightest. So if we do np.argsort weights, we'll get back the IDs of fish sorted from lightest to heaviest. So if we reverse that with square brackets colon -1, we'll get back the IDs from heaviest to lightest, and then we can assign that to a variable called sorted fish. Now, if we index the lokes array using sorted fish, it'll reorder the rows of lokes based on the weight of each fish. The heaviest fish has its new IJK location listed first, the second heaviest fish has its location listed second, and so on. Now, notice the duplicate locations here, like the zeros row here, the zeros row here, and the zeros row here. Well, the fish that's going to survive is the one that corresponds to this row, because it's the heaviest fish. So all these three fish are going to collide, but this guy is going to survive because the heaviest fish are listed first in this array. So what we want to do is we want to get the index of the first occurrence of each unique value in this array. And we can do that with np.unique, where we set return index equal to true. So we'll say uniques first indexes equal np.unique, and then we'll pass in lokes square bracket sorted fish. We'll set axis equals 0 because we want unique values across axis 0, in other words, unique rows. And we set return index equals true to get the first index of each unique value. And then we'll go ahead and print uniques, and we can print first indexes. So now if we say sorted fish, square brackets, first indexes, we'll get the ID of each surviving fish. You own a taco truck that's open 24/7, and you manage 5 employees who run it. Employees work solo 8-hour shifts. You decide the best way to set their schedule for the upcoming week is to create a bunch of random schedules and select the one that looks best. You build a 1000 by 21 array of random employee IDs where element ij gives the employee ID working shift J for schedule I. A schedule is valid as long as no employee works 2 consecutive shifts. Get the row index of all valid schedules. All right, let's see the solution that I came up with. And let's go ahead and break it down. So we want to compare adjacent values in each row and make sure that no 2 neighbors are the same. So for example, here you can see employee ID 0 works these 2 consecutive shifts for the first schedule. So this is going to be an invalid schedule. And there's 21 columns, which means that we want to compare 20 pairs of adjacent elements for each row. Now we can do that by picking out the first 20 columns and comparing that to the last 20 columns. In other words, the matrix that's offset 1 column to the right. So to do that, well, to pick out the first 20 columns, we can say schedules square brackets colon comma colon -1, which means pick out every row and every column up to but excluding the last column, and we'll check for not equals. So then we pick out the last 20 columns, and we can do that by saying square brackets colon comma 1 colon, which means give me every row, but only the columns starting from index 1 up until the end. So when we run this, we get a big Boolean array. It's a 1000 by 20 Boolean array. And then the true values are good. The true values mean that the adjacent employee IDs are not the same. So we want to identify rows where every value in the row is true. That means it's a good schedule. So what we'll do is we'll use the all function, and we'll say np.all, and then we'll pass in what we just built. And we want to do it for each row. So we'll say axis equals 1 because we want to check that the values are all the same or all true across axis 1. So when we run this, what we get is we get a big 1D Boolean array. It's a 1000 by array of Boolean values. So then the good schedules are going to be identified by true values in this array. And if you remember, false and true are synonymous with 0 and 1. So we can actually use the np.non-zero function to pick out all non-zero values, which again, for a Boolean array, it means it's picking out the true values or the indices of true values. So we'll say np.non-zero. And the non-zero function actually returns a tuple where it has one element for each dimension in the given array. In this case, we only passed it in a one-dimensional array, so we want to pick out the first element of the result. And that'll give us the indices of valid schedules. You manage a local department for the census responsible for measuring the population of each block in the city where you live. Even though you could do it yourself, for each of the last 5 years, you've tasked this job to your subordinate, Jim. What Jim gives you each year is a 2x4 array of his population estimates, where each element of the array represents a city block. After 5 years, you have a 5x2x4 array of population estimates called Jim, where IJK represents Jim's population estimate for block JK in year I. The thing is, you don't fully trust Jim's estimates because you see him spending an ungodly amount of time on Facebook. So each year, you go behind his back and measure the population of 2 city blocks. After 5 years, you have the following data. Blocks, a 5x2x2 array indicating which blocks you measured each year, where IJ gives the coordinates for the jth block you measured in year I, and pops, a corresponding 5x2 array with the population you measured for the jth block in year I. How many times was Jim's estimate at least 10% higher or lower than your estimate? So to make this more clear, these are Jim's population estimates. And so, for example, these are his estimates in the first year. These are his estimates in the second year, third year, and so on. And blocks and pops corresponds to your estimates. So for the first year, you measured these 2 city blocks, block 02 and block 13, and the population you came up with for this first block was 100. So your estimate of 100 corresponds to block 02, which corresponds to Jim's estimate of 92. And again, your goal is to determine how many times Jim's estimate was at least 10% higher or lower than your estimate. All right, here's the solution that I came up with. So let's go ahead and break it down. Now, our initial goal is to build a 5x2 array of Jim's estimates that correspond to our 5x2 array of estimates. But before we do that, let's reimagine the Jim array as a row of matrices, and we'll do the same thing with the blocks array. So if I want to subset the Jim array and get back a 5x2 array, I can do that by using 5x2 index arrays for the I, J, and K dimensions. So let's set up that framework. So here I'll say I equals, and then I'll pass in a list, and let's just initialize it with all zeros. So we'll do 0, 0, and we'll do 5 copies of that. And then we'll do the same thing for J and K. So these are index arrays that we're going to pass into the Jim array like this to pick out the elements that we want to fetch. So I here represents the year of the population estimates. So looking back at our pops array, well, the first row should just be year 0, and then we're going to pick out year 1, year 2, year 3, and year 4. Now, the J index array here is going to correspond to the first column of each nested matrix in the blocks array. So the values we want for the first year are going to be 0 and 1. So we'll say 0, 1. And then in the second year, it's going to be 1, 0. The third year will be 0, 1. And then 1, 0 again, and then 0, 1. And then the K index is going to correspond to the second column of each nested matrix in the blocks array. So in this case, we're going to pass in 2, 3, 2, 0, 0, 2, 1, 3, and 1, 0. Okay, so if we run this, we'll get back the corresponding population estimates that Jim got, which correspond to our population estimates. So how do we make this a little bit more dynamic? Well, let's focus on the J index array here. So what we're picking out with the J is we're picking out every matrix in the blocks array, every row of each matrix, but only the values in column 0. So we can replace this sort of hard-coded array with blocks, square brackets, colon, comma, 0. And then the K index array is nearly identical, except we're picking out the values in column 1. So that leaves us with the I index array. Now notice the duplicate columns here. So we can actually get rid of this second column. And what will happen internally when we do this index here is that I will broadcast to match the shape of J and K. Now, this array here we can represent with np.arange, open parens 5, square brackets, colon, comma, none. So remember, np.arange is just a 1D array, 0, 1, 2, 3, 4. And then square brackets, colon, comma, none just promotes that from a 5-by array to a 5-by-1 array. Okay, so once again, we have Jim's estimates. Let's go ahead and assign that to a variable called Jim_pops. So from here, the rest is fairly straightforward. If we do pops minus Jim pops, we get the difference between our estimates and Jim's estimates. If we wrap that in np.abs, we get the absolute differences. We divide by pops and we get the percent differences, or absolute percent differences. We'll check greater than or equal to 0.10 to determine which of them is at least 10% different. And then we can sum the true elements with np.sum and determine that 2 of Jim's estimates are at least 10% different than our own estimates. Given a 10 by 10 by 10 array of zeros, set ijk equal to 1 if all of the following hold true. I is odd, j is even, and k is prime. In other words, set these elements to 1. Okay, here's the solution that I came up with. Let's break it down. So the I indices that we're interested in are going to be the odd indices. So those are going to be 1, 3, 5, 7, and 9. J is going to be the even indices, 0, 2, 4, 6, and 8. And K will be the prime indices. So those will be 2, 3, 5, and 7. Now, the specific elements that we want are actually going to be the Cartesian product of these 3 arrays. So in other words, the combination of these 3. So 1, 0, 2, 1, 0, 3, 1, 0, 5, and so on. In total, it's going to be 5 times 5 times 4, so 100 elements that we want to update to 1. So if we try to do something like Chewy square brackets I comma j comma k equals 1, this actually will give us an error, and it's not at all what we want. What this is attempting to do is it's attempting to set element 102 as 1, then 323 as 1, 545, 767, and then lastly element 98, and then this is missing a k index, so that's where you get the error. But besides the fact that it errors, it's really trying to just update 5 values instead of 100 values. So what we want, like I said, is going to be the Cartesian product of these guys. Now, one way you can do that is with broadcasting. So if I do I square brackets colon comma none, this turns my 5 by array into a 5 by 1 by 1 array. And then if I do j square brackets none colon none, this turns into a 1 by 5 by 1 array, and k square brackets none comma colon becomes a 1 by 1 by 4 array. So NumPy will broadcast these index arrays into the following 5 by 5 by 4 index arrays. And you can imagine that they get zipped together into the following tuples, which pick out the exact elements that we want to update and set equal to 1. Now, there's a shorthand way to do this, and that's with the function np.ix underscore. And so if I say np.ix underscore and I pass in a sequence of 1D arrays like I, j, and k, it returns what's called an open mesh, which is exactly what we've done here. So then all I have to do is say Chewy square brackets np.ix underscore ijk, close square brackets, and set that equal to 1. And this statement here is equivalent to this statement here. So that's just the shorthand way to subset an array when you have 1D arrays and you want to sort of get the Cartesian product of these to select out specific elements. You're preparing for a game show where you play the following game. You're faced with 4 doors. Behind one door is cash money, and behind the other 3 doors is a steaming pile of broccoli. If you pick the door with money, you get the option to play again at the risk of losing the money you've collected thus far. If you keep winning, you can play a maximum of 3 rounds before the game show host kicks you off his show. You have some strategy ideas you'd like to evaluate before you go on the show. So you hired an unpaid intern to scour through historic recordings of the show and log data on where prizes were located and the value of each prize. Your intern gets back to you with the following matrices. Prize doors, a 5 by 3 array where element ij gives the door hiding the prize in the jth round of the ith game, and prizes, a 5 by 3 array where element ij gives the prize amount in round j of the ith game. Build a 5 by 3 by 4 matrix where ijk represents the prize behind door k of round j of game I. Okay, here's the solution that I came up with. Let's go ahead and break it down. So the first thing I do is initialize an array called answer. So answer is a 5 by 3 by 4 array of zeros, where this corresponds to the fact that we have 5 games. Each game has 3 rounds, and each round has 4 doors. And these values are like the cash prizes behind each door. So we want to update the values that we know have cash prizes behind them. And that's going to be given by the prize doors array and the prizes array. So let's start by sort of looking at the prize doors array. Now, these doors are actually indices. And so, for example, prize door 1, this means that in the first game, in the first round, the prize was behind door number 1. And that's going to correspond to the first game, first round, door number 1 is going to be this guy. So we'll want to update this value with the cash prize 100. So if we think about these doors where the cash prizes were hidden, well, this is game 0, round 0. This one represents game 0, round 1, game 0, round 2, game 1, round 0, game 1, round 1, game 1, round 2, and so on. So we can build corresponding 5x3 index arrays for the game indices and the round indices. So let's go ahead and do that. So if we say game indexes, and we'll set this as, again, we want to make it a 5x3 array. So 1, 2, 3, 4, 5. And so the games we're interested in are going to be 0, 0, 0, then 1, 1, 1, 2, 2, 2, 3, 3, 3, and 4, 4, 4. And then we can do nearly the same thing for the round indices. So the rounds in this case are going to be 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, and 0, 1, 2. And again, I'm building these indices so that they sort of line up with the prize doors array that we already have. So now what we can do is we can say, well, answer square brackets, and we'll pass in our 3 index arrays. So game indexes, round indexes, and prize doors. And we set that equal to the corresponding prizes. So this actually gives us the solution. We're just not satisfied because it's hard-coded. So how do we make these arrays a little bit more dynamic? And we can do that with broadcasting if we set up the appropriate row or matrix and row indices. So np.arrange 5 square brackets colon comma none is going to give us this array here. So it's a 5x1 array. And then np.arrange 3 square brackets none comma colon is going to give us this 1x3 array. So these two arrays, when we pipe that into the square brackets here, they're actually going to broadcast, and this column is going to get copied 3 times, and this row is going to get copied 5 times. So they're going to be identical to the game indexes and round index arrays that we set up earlier. But this way it's a little bit more dynamic and easier. So putting it all together gives us my original solution. Given peanut, a 4x5 array of zeros, and butter, a 5-element 1D array of indices, fill the rows of peanut with 1s starting from the column indices given by butter. So for example, in the first row of peanut, you're going to start at column index 3. That's going to be here. And you're going to replace these zeros with 1s. In the second row, you're going to start at column index 0. So you're going to replace the entire row with 1s. In the third row, you're going to start at index 4. So you're just going to replace this guy with a 1. And then the last row, you're going to start at column index 1. And you want to replace these 4 zeros with 1s. Okay, here's the solution that I came up with. Let's break it down. So to start, we're going to build 2 arrays that match the shape of peanut. So the first array I'm going to build is called col indexes, and I'll say that equals np.array, open parens, open square brackets. And then I want to get the corresponding column index for each value in Peanut. So the corresponding column indices in row 1 are going to be 0, 1, 2, 3, and 4. And then of course they're going to be the same thing for each row after that. So then I want to build another array, a 4x5 array, that gives the corresponding values from butter that we want to associate with each value in Peanut. So I'll say butter expanded equals np.array, open parens, open square brackets. And so in the first row, we want to use the value 3. So I'll just say 3, 3, 3, 3, 3. And in the second row, we're going to use the value 0. So I'll do the same thing. I'll just repeat the value 0 5 times. Third row is going to get the value 4. Fourth row is going to get the value 1. Okay, so now if I make the comparison and I say butter expanded is less than or equal to col indexes, I get back a 4x5 Boolean array where the true values tell me if the column index is greater than or equal to the corresponding value from butter. And these are exactly the values that we want to overwrite with ones. So for example, in the first row, we want to overwrite these zeros with ones because they occur at column index 3 and 4. And so you can see that's why these two values are true while these 3 values are false. So we could use this Boolean array to subset and make a replacement in the Peanut array, but an easy trick that we can do here is just convert the Boolean array to integers, or actually floats, basically zeros and ones. So we'll say this dot as type, open parens, quotes, and the reason I'm going to use floats here is to match our input type. So you can see the decimals indicating that Peanut is an array of floats. So I'll say open quotes float 64. And this gives me the desired output. Now, what we want to clean up is this array and this array. We want to make these a little bit more dynamic. So let's suppose for a second that butter expanded. Well, there's a lot of repetition here. So let's just make this guy a 4 row by 1 column array like this. And you can kind of see the repetition here as well. So we'll reduce this to a 1 row by 5 column array like this. And I'm going to go ahead and insert a new cell here. And so now if we do butter expanded is less than or equal to col indexes, the result of this actually broadcasts to the exact Boolean array that we wanted. So how do we build these arrays a little bit more dynamically? Well, butter expanded, oh, and let me back up a second. Col indexes here is a 1 row by 5 column array. It's a 2-dimensional array. It actually doesn't even need to be 2-dimensional as long as butter expanded is 2-dimensional. If this guy is 1-dimensional, that's good enough for the broadcasting to work as we want it to. So instead of doing this, we could simply replace this with np.arange and then the number of columns in the Peanut array. So we'll say peanut.shape square brackets 1. And let's go ahead and print col indexes. And then here, well, this comes from the butter array. So what we'll do here is we'll say butter open square brackets colon comma none. And this reshapes the butter array into a 4 row by 1 column array. And then we just kind of put those pieces together to get this statement here, which gives us the result. Given a 1D array of integers, One-Hot-Encode it into a 2D array. In other words, take this array called yo-yo-yo and use it to build an array like this. Alright, I came up with two solutions to this problem. So here is my first solution. And let's go ahead and break it down. So the first thing I do is I set num classes equals np.max yo-yo-yo plus 1. So in this case, let me go ahead and print this. The max value of yo-yo-yo is 3. So we assume that there are 4 classes, specifically 0, 1, 2, and 3. Then the second thing we do is we use this function called np.I, which creates a square matrix of zeros with ones along the diagonal. So for example, if we say np.I 8, then we get an 8 by 8 matrix of zeros with ones along the diagonal. So we use this function and we pass in the value num classes. So in this case, we get a 4 by 4 array of zeros with ones along the diagonal. And you can think of each row of this matrix as representing the one-hot-encoded values of each of the categories or each of the classes. So for example, the first row here, it's the one-hot-encoded representation of class 0. The second row is the one-hot-encoded representation of class 1, and so on. So what we want to do is we want to pick out the rows from this matrix based on the values given by yo-yo-yo. So we just say np.I num classes square brackets yo-yo-yo, and that gives us our desired result. Okay, here's my second solution. So the strategy here is to initialize an array of zeros and then fill it with ones in the correct locations. So in this case, the values of yo-yo-yo correspond to the columns in the output, and the indices of yo-yo-yo 0, 1, 2, and 3 correspond to the rows of the output. So we know we need to initialize an array of zeros that is num cases by num classes in shape, where num cases is just the length of yo-yo-yo, and num classes is the max value of yo-yo-yo plus 1, so 4. So our initial array of zeros looks like this. And then if we just think about the first couple of values of yo-yo-yo, so this 3 means that in the first row, we want to replace the value at index 3, so this guy, with a 1. This 1 means the value in the second row, index 1, we want to replace with a 1. Here, the 0 means the value in row 3, index 0, we want to replace with a 1, so this guy. So the way we can sort of write this out is we can say result square brackets, and then what we want is we want the array 0, 1, 2, 3, and then the values in yo-yo-yo, and we want to set those equal to 1. And then of course we can make this a little bit more dynamic by saying np.arange num cases. And then if we print the result, you can see we get our desired solution. Your job is to monitor the rainfall in a region that you've broken into a 3x4 grid. Every time a storm comes, if a cell in the grid gets rain, you record it. At the end of a month, you have the following two arrays of data. Rain locations, a 7x2 array representing the location of recorded rainfall, and rain amounts, a 7-element 1D array representing the amount of rainfall in each corresponding location. Build a 3x4 array representing the total accumulated rainfall in each cell of the grid. Oh, and don't use a for loop. Okay, here's my solution. Let's go ahead and break it down. So the first thing we do is we initialize a 3x4 array of zeros, which we'll call rainfall. And basically this array is going to store our result. So what you might be inclined to do at this point is something like the following. So you might say rainfall square brackets, rain underscore locations, square brackets, colon, comma, 0, rain underscore locations, square brackets, colon, comma, 1, and you might say plus equals rain amounts. And what you're trying to do here is you're saying, okay, in the rainfall array, we want to update the values at indices. Well, rainfall locations, square brackets, colon, comma, 0, these are going to be the row indices of the values you want to update. Rain location, square brackets, colon, comma, 1 picks out the column indices of the values you want to update. And then plus equals rain amounts is going to cumulatively add the rain amounts that correspond to those locations. Now, the problem is this doesn't work. And where it fails specifically is the elements of rain locations that are repeated. So for example, index 2, 3 is repeated 3 times. And if we look at that location, which is this guy, the amount of rainfall in this result is actually equal to the last rain amount in that location. Another example would be element 1, 1, which is repeated twice. So this amount of rainfall that we ended up with is 0.4. I'm sorry, it's actually 2.0. Well, that's the last amount of rainfall that it got, but it actually received other earlier rainfall. So this plus equals, assignment or update statement doesn't work like you might think it does. So NumPy's solution to this problem is the .at method, which exists for all unary functions. So in this case, what we can do, the way we can modify this, is we can say np.add@, and then we pass in the array that we want to update. Let me go ahead and rebuild this rainfall array. So the array we want to update is the rainfall array. Then we pass in the indices where we want to update it. So in this case, we give it a tuple of row indices and corresponding column indices, and then the corresponding amounts that we want to add. So rain amounts. And when we run this, now you can see that this function works as we desired. After a series of poor life choices, you find yourself managing a recreational table tennis league. There are 10 participants, and in an effort to make the first round of matchups as exciting as possible, you develop a model that predicts the score difference for every possible pair of players. That is, you produce a 10 by 10 matrix where ij represents your prediction for player i's score minus player j's score if they were to compete. Given this matrix, determine the best matchups for round 1, the matchups that minimize the sum of squared point differentials. Okay, here's the solution that I came up with. And it's pretty long, but let's go ahead and break it down. So one way we can approach this problem is by thinking about every possible schedule. So every possible schedule is just going to be every set of possible matchups between players. And just to give you an idea of what these might look like, obviously there's going to be many more than this, but an example schedule would be player 0 versus player 1, 2 versus 3, 4 versus 5, and so on. So if we imagine every possible schedule, there's going to be quite a few of these. And the question really is, how do we even build an array that represents every possible schedule? So let's start by thinking about the array of unique player IDs. So let's think about this array here. And I've sort of structured this so that you can imagine adjacent elements as representing a match. So for example, the first 2 indices or positions represent the first game. So that's going to be between player 0 and player 1. Then the next 2 elements represents the second game. So this will be between player 2 and player 3, and so on. So if we have this array, imagine every possible permutation of this array. So that's going to be 10 factorial permutations. So that's almost going to be every possible schedule. The problem with this is that we'll end up with duplicates. So for every matchup, for example, the matchup 0-1, there's a duplicate matchup, which in this case would be matchup 1-0, where these are really it's the same two players, so it's the same matchup. So there's actually 10 factorial divided by 2 number of unique schedules that we can consider. And to extract these, we can just say that we're only interested in matchups where the first player has a smaller ID than the second player. So how do we even build all of these permutations? And this is one of the few times that I'm going to use a tool from another package. So to do that, we're going to say from itertools import permutations, and then we'll build this perms array using np.array list permutations and then the list of unique player IDs. Then we can go ahead and print perms. Now this does take a second to run, but when it's finished, you'll see that we have this really big array. It's going to have 10 factorial rows of every permutation of these IDs. So the next thing we're going to do is we're going to partition that array into 2 matrices that represent player 1 and player 2 for each game. So player 1 is going to be the player at indices 0, 2, 4, 6, and 8. You can kind of see that in this example we gave up here. And player 2 is going to be located at indices 1, 3, 5, 7, and 9. And then the matchups we want to keep are going to be the ones where player 1, his ID is less than player 2's ID. So we'll say keeps equals np.all, p1 less than p2, and we're going to check that along axis 1. And then we'll set p1 as p1 square brackets keeps and p2 as p2 square brackets keeps. So basically that's going to pick out the permutations where player 1 is less than player 2 for every game in the presented schedule. Okay, so it's going to cut this matrix in half, basically. Okay, so then we want to build a matrix where ij gives the expected point differential for the jth pairing in the ith schedule. So what we do here is we use this score diffs array here, and we already have the indices for player 1 and player 2. So just to get the point differentials, all we have to do is say score diffs, square brackets, and then we'll use P1 to get sort of like the row index and P2 to get the corresponding column index. And let's go ahead and print this out. Okay, so these are the point differentials between pairs of players. And then we want to get the sum of squared point differentials for each potential schedule, so each potential set of matchups. So what we'll do is we'll say schedule scores equals np.sum, and then we're going to take the squared point differentials, and we're going to calculate that sum along axis 1, so along the column axis. So we get back this big array of squared score differentials. And then we want to find the schedule that has the smallest sum of squared point differentials. There could be multiple ones, but we're just looking for one of them. So we'll say best index equals np.argmin schedule scores. And that'll give us the index of the smallest value in this array. And then we'll set the best. So actually, let me do this first. Okay, so apparently the best schedule happens at index 16,490. So then to represent the best schedule, basically we identify the who player 1 is for this schedule, or the set of player 1s, and the set of player 2s, and we'll just stack them vertically with vstack. So once we do this, we can print the best schedule, and we can see that it's player 0 versus player 7, 3 versus 6, 1 versus 8, and so on. And just to do a sanity check here, let's take a look at player 0 versus player 7. So player 0 versus player 0, 1, 2, 3, 4, 5, 6, 7. Well, they have a score difference of negative 2.15. I mean, if you look at this whole matrix, you can see that's a pretty small number, so that's a good sign. Let's check player 3 versus player 6. So we have 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6. So their predicted point differential is 2.24, another pretty small number. So it looks like we did this correctly, and we can have the most fun, most optimal start to our table tennis league. Given a 1 million element array where each element is a random character in A to Z, identify the starting index of every sequence of characters that spells Waldo. Twist. Include sequences where 4 of the 5 characters match. For example, Wafdo and Zaldo, but not Wadlow. Okay, here's the solution that I came up with. And let's go ahead and break it down. So the key to this solution is this Windows array. So let's go ahead and take a look at this guy. So Windows represents 5 character sequences from the chars array. So for example, the first row in Windows is ARPBX, which is the first sequence of 5 characters in this array. The second row in Windows, RPBXF, is the next sequence of 5 characters. And notice that it's only 1 character offset from the first sequence of 5 characters. So the way we build this array is we use the asStrided function, where we tell it we want to build a view from the chars array. We want the shape of the output to be the length or the number of characters in chars minus 4, because that's how many sequences of 5 characters we can get, by 5 columns, because we want to look at sequences of 5 characters. And then the strides parameter here, well, wherever you are in the Windows array, we basically tell NumPy that to get to the next row, it needs to look across this many bytes of data, where chars.strides square brackets 0 is just the number of bytes in any given element. So if we're at element P, to get to the next row, we're basically telling NumPy to only move across one element, or to sequence or iterate across one element. So that's why rows go just offset one element from each other in the chars array. And then of course we do the same thing for columns, because they're just offset one character from each other as usual. So the next thing we do is we build an array called Waldo with the characters in the word Waldo. And then we want to compare these characters to these characters. So we want to compare Waldo to Windows. So we say Windows equals Waldo, and we get back a big Boolean array like this, where, for example, the first false value here means that W is not equal to A. And we're interested in rows of this Boolean array where at least 4 of these values are true. So those are going to be cases where at least 4 letters in Waldo match the letters in the Windows array. So we'll say Windows equals Waldo dot sum across axis equals 1, so across the columns, and we want to pick out indices where those sums are greater than or equal to 4. Now this is going to return a tuple, And since this array here is just one dimensional, we're only interested in the first result in that tuple. So we'll say square brackets 0. And this is going to give us the indices of what we want, the cases where at least 4 of these characters match a sequence in the Windows array, which are just sequences of 5 characters. Now, if you want to check this, you can run a little block of code like this. So we'll say for index and start indexes. So we'll assign this to the value start indexes. So for index and start indexes, we'll just print empty quotes dot join cars between start index and index plus 5. And you can see that these do indeed pretty closely match Waldo, like Waldo, Wallio, Walfo. And if anybody's expecting a child on the way, maybe this is a neat little set of potential names for your future kid. Especially if you're a celebrity, I think these would go over really well. Calculate the element-wise outer product of 2 matrices A and B. So the result should be a 10 by 3 by 5 array, where the first submatrix should look like this, because it's the outer product of the first row in A with the first row in B. All right, so if you did some Googling for this problem, you may have stumbled across this Stack Overflow post, which is completely where I got this problem from. And I have 3 solutions, but the first 2 solutions, I give total credit to Dvarkar. Hopefully I'm not butchering that name too badly. But he came up with 2 very elegant solutions, and then I have a third solution as well. So I kind of have those solutions organized like this, which I will copy and paste. And then I'm just going to talk about the basic strategy for each of these guys. So the first one uses broadcasting, and A initially is a 10 by 3 array. So you can see that here. And so if we do A square brackets and then ellipses, this is equivalent to saying A square brackets colon, comma, colon, but it's sort of like shorthand notation, comma, none. Well, that's going to insert a new last axis into A, and it's going to convert it into a 10 by 3 by 1 array. And then B is a 10 by 5 array, but we give it a new second axis. So we convert it from a 10 by 5 array into a 10 by 1 by 5 array. And then when we do this multiplication between this modified version of A and B, you can imagine that A, the 10 by 3 array A, gets copied 5 times along the last axis to conform to B, which gets copied 3 times along its second axis. So if you just pick out a single row, let's say like the first row here, this guy gets copied 5 times along the last axis, and this guy here gets copied 3 times along the second axis. And those get multiplied, and that produces the outer product of the first element of A and B. And so hopefully you can kind of see how this works out to produce an element-wise outer product. Now, the second solution here uses an Einstein sum. And I like to write these out in pseudocode. So the subscripts I and J correspond to the rows and columns of A. The subscripts I and K correspond to the rows and columns of B, and the subscripts I, J, and K correspond to the indices or the axes of the output. So what I'll say in pseudocode, you could write this out as initialize output as an array of zeros with shape. Well, I is going to span 10 different rows of A, so 10. J is going to span the 3 columns of A, so it's a 10 by 3, and then K here is going to span the 5 columns of B. So we initialize an array of zeros with shape 10 by 3 by 5, and then we iterate over each unique subscript. So we say for I, for J, for K, and then we set output underscore IJK. So the IJK element of the output, we set that as plus equals A ij times b ik. And I realize this is probably a little confusing, but if you just take the time to work this out in your head and maybe fix I to some particular row of A and B, you can see that this is indeed the outer product of A and B. And then the last solution, which is the one that I came up with, is to use the as-strided function, where basically if you think about the output, and let's think about a particular element of the output. So we'll say, output ijk. Well, this is equal to some element of A times some element of B. And so if you imagine we can reshape A into an array that is the same shape as the output. So we want to reshape A into a 10 by 3 by 5 array, and we want to reshape B into a 10 by 3 by 5 array, then output ijk we can say is equal to aijk times bij. So that's really the strategy to this solution. And the function as-strided, if we pass in the correct parameters, we can create a view of A where the ijk element of A points to the correct element of A that we would want to multiply with the corresponding element of B to get to the corresponding output element. And so since these are not actually A and B, they're views of A and B, we'll call this AS and BS. And their product will give us the element-wise outer product. So hopefully that wasn't too confusing. I didn't want to go into too much depth because I talk about each of these topics in the course. And if you're confused on any one of these, you can go back and look at the details in the course. But one last thing, so if we want to just see these in action, it's kind of interesting to think about which one of these solutions would be fastest. So we can use the magic command %timeit and then do something like, so I'll say OP1 for outer product 1 equals outer prod broadcasting A comma B. And we can see how long this takes. And then we can do the same thing for the einsum and for the stride trick version. And you can see that the broadcasting and the Einstein sum are basically equivalent. This one's a little bit faster, it seems, but they're more or less the same. And then the stride trick is actually significantly slower. So tip your hat to Devarkar, who came up with those really good solutions.